All righty, there we go. So, basically in this section, and we can go back to the first page, we are talking about how to solve trigonometric equations. We looked at a few examples in the handout last time, and, maybe one or two examples from the textbook. So, just different types of equations and how we can solve them. So that's kind of what we were looking at. So we need to pick up from this next type of example here, where you are given, as you look at this example, 2 times sine squared x plus 3 times cosine of x minus 3 equals 0. So you actually have both sine and cosine functions in this equation. And, obviously we will need to convert them into one single trigonometric function before we can solve them. So in this case, what we normally do is we are going to take the sine square and convert it into a cosine function because, we can use the Pythagorean identity over here. And, I think I have that page open. Yeah, right over here. So you see, we can go ahead and use this identity, get sine squared by itself, move cosine to the other side, and then we can use this to make the substitution happen. So that's exactly what we do. We take sine squared equal to 1 minus cosine squared x, replace that over here. So you can see you end up getting 2 times 1 minus cosine square of x. Go ahead and distribute that 2. So 2 times 1 is going to be 2. 2 minus 3. That should actually be a negative 1 there. Okay. So basically go ahead and distribute that 2. So you'll end up with 2 times 1, which is 2, 2 times cosine squared of x. And I can see actually what happened here. So you end up getting 2 minus 2 times cosine square of x. And then, of course, plus 3 cosine of x and minus 3. So since there is a negative on this 2 times cosine squared of x, we actually take the entire equation and multiply it by negative 1. And you can see they're telling us that over here in the instructions. So that will end up making this negative 2. This will become positive 2 cosine squared of x. And you can see that here. The positive 3 will become negative 3. And the negative 3 will become actually positive 3. So when you take positive 3 and subtract negative 2 from it, that's where this positive 1 is coming from. So there's actually a step in there that they have skipped, but they're telling you in the instructions what they ended up doing. So that's kind of how this guy ended up being a positive 1. This one ended up becoming negative, and technically this guy should have been a negative, but then it ends up becoming positive. Once you convert it into this format where your entire equation is now with cosine function, you are actually using regular factoring techniques. So think about this, we can replace this guy with, I don't know, let's say t. So cosine of x, we can say let that equal to t, think of this as a substitution. So that means cosine square will become t squared. So you end up getting 2 times t squared minus 3 times t plus 1 equal to 0. And then we can use, factoring techniques to help this out. So this guy will factor into 2t and t. The plus 1 will actually factor into minus 1 and minus 1. And the reason that happens is when you have a plus here, but minus in the middle, that means both your factors are actually going to have a minus sign, because remember, when you go back and FOIL, you should come back to the original equation. So 2t times t will give us 2t squared, which is this first term here. 2t times minus 1 will be negative 2t. Negative 1 times t will be negative t. And then negative 1 times negative 1 will be positive 1. And then when we combine the two center terms or middle terms, you get negative 3t, which is this term over here. And then, of course, you end up getting plus 1. So that's kind of where this guy will factor into, is the 2t minus 1 and t minus 1. And when you translate that t into cosine, you will end up getting 2 times cosine of x minus 1, cosine of x minus 1, and that's where this factoring came up from. So you are, again, remember how we were talking about last time that we still end up using a lot of those algebraic techniques to help out. So here you are actually going to use factoring to help you simplify this. So first step is converting that sine square into a cosine value. So you can see we use the Pythagorean identity here to rewrite sine square of x as 1 minus cosine square of x. So now that our trigonometric function comes out to be all in cosine square, then we can use factoring to simplify that. And then remember, we had talked about the zero factor property. So you take each factor, set it equal to 0, and then from each side, you will end up getting a solution. So you are ending up with x equals 0, x equals pi over 3, and x equals 5 pi over 3. Because remember, when you have 2 times cosine of x minus 1 equal to 0, get the cosine by itself. So we start by adding 1 on both sides, and then divide by 2. So for which x value is your cosine function going to be equal to 1/2? So you try to find those. For the other one, cosine of x minus 1 equals 0. This is simple. Just move 1 to the other side, and you end up getting cosine of x equals 1. So again, for which angle, which value of x is your cosine function going to be equal to 1? And for these guys, it may not be a bad idea to have your unit circle handy. So let's see, cosine is going to be equal to 1/2 right over here. So that's the pi over 3. And 1/2, 5 pi over 3. So from this one over here, you are getting x equals pi over 3 and 5 pi over 3. For cosine equals 1, cosine equals 1 is going to be right here. So that's going to be an x value of 0 for this guy. So that's where you got the 0, the pi over 3, and the 5 pi over 3. So that's how you are coming up with this. And since we are doing this as a general solution, remember, you take the period of the cosine function and add that with your answer. So 0 plus 2n pi will just give you 2n pi, pi over 3 plus 2n pi, 5 pi over 3 plus 2n pi. So that's how you are going to go about solving these types of equations. So you've got another example here. So watch the video lecture for this to see how you can solve that. Let's see. Actually, I think the example that I have may be based on this example over here. So this one is talking about how sometimes you may have to square each side of your equation to be able to, come up with a solution. And they're talking about to obtain an equation of the quadratic type. What happens in this case is because you are introducing a square on each side of your equation, that actually means you will end up with extra solutions. So that's what we call as extraneous, because they do not actually solve the original equation. They solve the equation after you have squared it. But if you were to try and solve the original equation, that would be an extra solution. It wouldn't solve the original equation. So whenever you end up using this technique by taking square on each side of your equation, you're going to end up in extra solutions. So they're telling us, make sure after you have found the solutions, check them in the original equation to make sure if they are valid or they are extra, extraneous. So if you look at this example over here, you've got cosine of x plus 1 equals sine of x. And this one, they're specifically asking us to find the solution in this interval. So they're not asking you for a general solution. They want us to stay in this interval here. So remember that. So in this case, there is not going to be any identity that we will be able to use to write this entire equation either as sine or cosine, because, we don't really want to have both sine and cosine in the equation. So this is the reason why we actually have to go ahead and square each side of the equation. Because, remember, if you have the sine square, then we can use 1 minus cosine square or vice versa, but there's no square on any of these trigonometric functions over here. So that's why we're unable to use any identity. So you will see what we end up doing is we take a square on each side. So that gives you sine square of x. On the left-hand side, guys, again, you are using algebra. So if you have a plus b, the whole quantity squared, remember you multiply the binomial term into itself. So you're not just doing square and square on those numbers. That's not how this works. You actually will do FOIL. So you are taking cosine of x plus 1 and multiplying it with cosine of x plus 1. So you will use FOIL to multiply this. And that's what ends up giving you this left-hand side, okay? Now that you have your cosine square of x plus 2 cosine x plus 1 and then sine square on the other side, well, now I can use my Pythagorean identity and rewrite that sine square of x as 1 minus cosine square of x. And now you will see our entire equation only has cosine. And this is very crucial, you know, when you're solving these trigonometric equations, you want to convert them into one single trigonometric function. Then, you know, of course, bring everything on one side. So as you can see, we took this one to the other side, it became minus 1. We took the negative cosine square to the other side and it became positive cosine square. So combine your like terms, which ends up giving you 2 cosine square of x. Middle term, of course, 2 cosine of x, and plus 1 minus 1 cancel each other out. So clean up your equation. And then whatever you are left behind with, that's what you are solving. So since we have cosine square over here and cosine over here, both of these have a 2. Take those outside as your greatest common factor. So you will be left with 1 of the cosine from here. And then since this entire term got taken outside, remember you put 1 as the placeholder. So factor it out and then, you know, take each of the factors, set it equal to 0, and then whatever answer you get from there. The only extra thing you got to remember here, guys, is that extraneous solution. So remember these answers that you came up with. So this answer that you came up with, the pi halves, 3 pi halves, and the pi, all of these are technically solutions for this equation over here, not this one. So these 3 solutions we came up with is for this one. So remember, you have to come back and check in the original equation to see if all of them are going to work or not. And here you can see how they're going through the checking. So, you know, we replace x with the pi halves, replace x with the 3 pi halves, and replace x with pi in the original equation. And then you have to see, will your left-hand side match the right-hand side? So as you can see, this guy checks out, which means this guy is a solution. Here you got positive 1 on the left-hand side, but negative 1 on the right-hand side, which means this guy does not check out, and this is your extraneous solution over here. And then for the last one, you are getting 0 and 0 on both sides because these guys cancel out, giving you 0. You've got 0 here. So this is your solution, which means 3 pi halves was extraneous. In the interval 0 to 2 pi, you only have 2 solutions, and they are going to be exactly at pi halves and pi. And guys, you will remember, since this is not a general solution, since we're only doing this in the interval from 0 to 2 pi, we are not adding the, you know, 2 and pi to this, because this is only when they ask you for a general solution. But when they ask you specifically for an interval, you don't add the 2 and pi. Okay, so be careful about if they specifically ask you within that interval. So that's kind of what happens with these types of examples where, you know, you don't have a square, you're not able to use any of the identities, then we're actually bringing this idea of converting it into a quadratic equation and trying to solve it from there. So let's pick an example for this guy, and let's see. This is section 2.3. I was looking at some examples earlier so we could kind of pick some to work on. So the instructions here are saying find all solutions for the equation, and they are asking us to specifically stay in this interval from 0 to 2 pi. So we're not going to be doing a general solution. We're just going to stick with specific ones. And the example that I picked was actually number 40 over here. So that's the guy down here at the bottom. Secant x plus tangent x equals 1. So again, you will see there are no squares on our function. You just have a basic secant of x plus tangent of x equals 1. Now for these types, and I purposely picked this one without sine or cosine, so we could talk about this a little bit. So for this type of equation, you actually want to see if I can convert this into sine and cosine. And so you can see both with secant and tangent, we're actually able to make that conversion, right? So what we can do here for number 40, secant of x plus tangent of x equals 1. So we know secant is the reciprocal function for cosine. So I can rewrite this guy as 1 over cosine of x. Tangent, of course, from the quotient identity, we know tangent can be rewritten as sine of x divided by cosine of x. So I am actually going to rewrite secant and tangent. Now here's the cool part. You can see how both our denominators have cosine. So you already have a common denominator. So all we need to do is go ahead and add our numerators. You know, we're just trying to clean this up at this point. That's what we're doing. So now that we have the common denominator and we go ahead and add the numerators, let's go ahead and move that cosine to the other side. So we're going to go ahead and multiply both sides of our equation by cosine of x. And you know what this will do is help us get rid of that fraction. And you are just left with 1 plus sine of x. And you know, of course, 1 times cosine of x will give us cosine of x. So we've pretty much brought it to the same place as where this example kind of started at. So you had cosine of x plus 1 on one side, sine of x on the other, and we've kind of done that, but just in the opposite order. Now, this is where we will go ahead and square both sides of our equation. So go ahead and square. So remember, you will do FOIL on the left-hand side. Right-hand side, you're just multiplying cosine with cosine. So this will become cosine squared of x. On the left-hand side, and if you want to do it kind of on the side as scratch work, we are taking 1 plus sine of x and multiplying it into itself. 1 plus sine of x. So 1 times 1 will give us 1. 1 times sine of x. Sine of x times 1. And then sine of x times sine of x. Which will end up giving us, you know, combine those two middle terms. So 1 plus 2 times sine of x plus sine squared of x. And that's your left-hand side over here. So 1 plus 2 times sine of x plus sine squared of x. So here, guys, you will see on the left-hand side, we have the sine of x term, we have the sine squared term. So we are actually going to make the substitution on the right-hand side, and we are going to rewrite cosine squared of x using that Pythagorean identity as 1 minus sine squared of x. So you're going to rewrite this guy as 1 minus sine squared of x. And then, you know, we will be able to combine this with the terms on the left-hand side. So let's bring those guys down. So you want to get 0 on one side and move everything else to the other side. So we'll start by subtracting 1 here, which will combine with this guy here. We will add sine squared of x, which will of course go with this guy here. And then again on the right-hand side, the 1 cancels out, the sine squared of x cancels out, leaving us with 0, which is what we wanted. And then, you know, of course, you can go ahead and combine the left-hand side. So plus 1 minus 1 cancel each other out. The 2 times sine of x will stay as it is. And then we are adding sine square of x with sine square of x. So 1 plus 1 will give us 2. So you will see this guy honestly comes out to be very similar to this example over here that we just looked at, except the difference is we have sine as our function and this example had cosine, but a lot of the steps are still going to be the same. So start with factoring. Both my terms have a 2 in common. Sorry, what happened to my pen? There we go. So both of them have a 2 in common, and both my terms have at least 1 sine of x in common. So we're going to factor out the 2 and the sine of x, which means we're actually taking that entire first term out. So that is where we put 1 as the plus placeholder. Plus, we took the 2 from the second term outside. He's gone. Sine squared, one of the sine is gone outside, which means we are now just left behind with sine of x. So factoring. And now let's go ahead and clean this guy up. So you will take 2 times sine of x, set it equal to 0, or the other parentheses 1 plus sine of x, and set it equal to 0. Get your function by itself, so divide both sides by 2. So he cancels out. Sine of x is 0 when your x is what value? So we'll need to check that. For the other one, let's see, we want to get sine of x by itself, so obviously we'll subtract 1. And now we are saying, okay, so sine of x is equal to -1 when your x value is what? Okay, so this is cleaning up, taking care of what we need to. Now I need you guys to tell me what will these values for x be when sine of x is equal to 0 and when sine of x is equal to -1. So I want you to share your answers with me in chat. Don't send your answers just yet. I just want to give you guys a chance to get your answers ready, and then I'll ask you to put your answers in chat. So don't send it just yet. Hold on to your answers, and then we can compare and see what each one of you came up with. So when sine of x is equal to 0, what will the x value be? And when sine of x is equal to -1, what will the x value be? So just have your answers ready. Like I said, don't share them just yet. When I ask you to, you can send it in. And if it helps, let's see if I can pull up the, oh, probably not going to help with all that writing, but, open up the unit circle at your end. Okay, let's see those answers, guys. All right, I've got pi, 0, 3 pi halves, 3 pi halves, pi and 0, -1, 0, 3 pi halves, okay? So I know this is going to be a little bit of a challenge to see this through all my writing over here. Okay, so we're talking about when sine of x is 0, and I know it's a little difficult, but sine of x is 0 when your angle itself is 0. Also, sine of x is 0 when the angle is pi, and you guys definitely had that answer in there. So I've got, oh, where did my chat go? I've got 0 and pi. Okay, Darren, I see your correction there. Very nice. And then when sine of x is -1, so sine of x is -1 right here at the angle of 3 pi halves, because, of course, at 90 degrees or pi halves, it's actually a +1. So, it doesn't translate to both opposite angle. So yeah, very nice, guys. So let's come back over here. So when x is equal to 0 and pi, that's when sine is equal to 0. And when x is equal to 3 pi halves, that's when sine is equal to -1. Now remember what we talked about, because when you take a square on both sides of your equation, you always end up getting those extra solutions. So remember these three answers, and let's highlight them in red. So these three answers are technically the solution to this equation over here. We need to check them for the first one. So we still have to do that checking. And I kind of wish now I had done this on the notebook instead of here, but let's go ahead and check this over here. So we'll start with x equals 0. So you will do secant of 0 plus tangent of 0 equals 1. And you want to see if you get a true statement or not, right? The left-hand side has to match the right-hand side. So can you tell me secant of 0 added with tangent of 0, if that will give us 1 or not? And you should be able to do that very quickly on a calculator. Just make sure your calculator is in the right mode. Okay, I'm seeing something come through. Lucy, yeah, very nice, because tangent of 0, you can kind of think of that as being 1 over cosine of 0, right? I mean, you can still use that reciprocal property plus tangent of 0. 1 over cosine of 0 will, of course, be 1 over 1. So you end up with 1 plus 0 equals 1. So you will get 1 equals 1. So that guy will check out. Our other one was x equals pi. Probably should use pi. Same thing, secant of pi plus tangent of pi equals 1. Will that check out? And obviously, again, you can do 1 over cosine of pi if you wanted to for this guy. So what do you say? Does this check out? Do we have a solution with pi or no solution? Or extraneous solution? What do we think? Andrew, you're saying no, it will be -1. Yeah, very nice. So 1 over cosine of pi. And again, you can use the unit circle for that. I mean, you can see cosine of pi gives you -1. So 1 divided by -1 will obviously give you -1 here. Tangent of pi is still going to be 0. So you are actually getting -1 equals 1, which is not a true statement. So pi is not the answer. And then our last one was x equals 3 pi halves. So same thing, secant of 3 pi halves plus tangent of 3 pi halves equal 1. So again, you can do 1 over cosine of 3 pi halves. Are you getting a true statement here or no? Okay, let's see. I've got Lucy. You think it's undefined, so no. All right, for this one, we definitely want to try and go back to our unit circle. So you will look at, when you have 3 pi halves, you will see your cosine is actually 0. So when you try to do 1 divided by cosine of 3 pi halves, you're actually doing 1 divided by 0. And like Lucy mentioned, that is actually going to be no solution because, you can't really simplify 1 divided by 0. So it doesn't matter what you even get for tangent, or you don't get anything for tangent, but tangent will also actually come out to be undefined. You are going to end up getting no solution from here, which means this is also an extraneous solution. So the only thing that worked out was that first one, x equals 0. So x equals 0 is the only solution you have. This guy is an extraneous solution. This guy is an extraneous solution. So pi and 3 pi halves are both gone. And it's only x equals 0 that works out. So you can see in this case, out of 3, only one of them worked. The other 2 were extra solutions. So these problems will take a little bit of patience and time, just because you have to go through all those different steps, different algebra to solve this. But, obviously we are able to find the solution with a couple extra ones in there. So questions on this example over here, guys? Okay, alrighty. So let's go ahead, clear this out. We'll go back to our handout here. And again, remember, since this was in the interval 0 to 2 pi, we didn't do the plus 2 and pi again. If they don't give you the specific interval and they just ask you to find the solution or solve the equation like they did over here, then this is where, since they don't give you a specific interval, we go ahead and add that 2 and pi for our general solution. So just, keep that difference in mind. Okay. Alrighty, so these next examples, we're actually getting into multiple angles over here. So far, in all the examples that you saw, you just had sine of x or cosine of x, right? With these examples, you will actually see you have something like 3t or 3x. It's not just the variable t by itself, it's got a number in front of it. So we're saying trigonometric functions that have multiple angles, which will be of this form, cosine of ku or tangent of ku, where k is actually going to be your coefficient, some kind of number. So they're saying basically to solve equations of these forms, you first solve the equation for ku and then you divide your result by k. So how to solve, these multiple angle functions. So let's take a look at this guy over here. We are given 2 times cosine of 3t minus 1. We still want to isolate the cosine function first, before we start worrying about that multiple angle. So you will see we start by moving that 1 to the other side, then we divide by 2 and move that to the other side. Once you are cleaning up and you only have the trigonometric function left to one side, then this is where you again kind of want to solve it like we just did. Where is our cosine function going to equal 1/2? What value is that going to be? So of course we know cosine is going to be 1/2 at 3 pi halves, pi over 3, and the cosine function is going to be 1/2 at 5 pi over 3. So using that, you can see we are coming up with, so 3t is going to equal pi over 3 and 3t is going to equal 5 pi over 3. So first solve this equation, and then once you get down to this stage, then of course we will end up dividing by 3 to get the t by itself. And since we're doing these as general solutions, we're again adding that 2 and pi at the end of these numbers. And now you can see when we divide by 3, right, which means everything has to be divided by 3, or same thing as multiplied by 1/3. So you will see when I do that, 3 times 3 will become 9. That's where the 9 came from. And then you end up with 2 and pi over 3. Same thing here, 3 and 3 will multiply to give you 9, and then this will end up becoming divided by 3. So that division by 3, or whatever that multiple angle value will be, is pretty much the very last thing you're going to do. So solve your equations like you normally do, and then worry about getting your x or t, or whatever the variable would be by itself. So before we look at example for this, I also wanted to show you another multiple angle equation, but this time you are given a fraction. So you actually have 3 times tangent of pi, or sorry, that's an x divided by 2 plus 3. Same thing, get the tangent function by itself. So we start by subtracting the 3, move him to the other side. Then we divide both sides by 3, and you end up getting -1. So again, where is the tangent function going to equal -1? And this is where you're thinking of tangent as more as sine divided by cosine. Where is this going to equal -1? So find that, and that's going to happen at 3 pi halves. So once you get 3 pi halves as your angle value, then we can go ahead and get rid of that 2. So in this case, since we are doing x divided by 2, to get rid of that 2, of course, we'll end up multiplying by 2 on both sides. So you will see, since you are taking 3 pi over 4 and multiplying it by 2, 2 will cancel out into 4 2 times. That's why this denominator became a 2. And tangent has a period of pi. So that's why you're only adding n pi over here. And then when we multiply this 2, that's how this guy ended up becoming 2n pi. So just, different way of using that multiple angle, but ultimately same thing. In the first example, we divided by 3. In this case, we multiplied by 2 because we had 2 different formats of that multiple angle measurement. So again, you've got examples for these in your handout that you can look through, but let's pick our examples here from the textbook. So for this guy, multiple angle, let's look at, how about 44? Okay. So 44, you can see we are given secant of 4x minus 2 equals 0. So we again want to isolate our secant function first, to start by moving that 2 to the other side. So we'll go ahead and add him, which will clear this out, leaving us behind with, let's see, secant of 4x equals 2. Now, obviously, if you want to use the unit circle, we have to use the cosine function again. So rewrite that secant as 1 over cosine of 4x equals 2. And this will again take a little bit of algebra to clean this up. So if you're comfortable doing this, go ahead and do this. But if you're not sure how to do this, then you can watch me. So here, since your cosine of 4x is in the denominator, we basically really need to switch places between the 2 and the cosine of 4x. So start by multiplying both sides by the denominator, cosine of 4x. Which will leave us with 1 equals 2 cosine of 4x. We obviously want to isolate the cosine function, so we'll divide both sides by 2, get rid of him, and you basically end up with 1/2 equals cosine of 4x, or you can write it as cosine of 4x equals 1/2. Just switching your left and right sides. All righty, so now we are looking for where is the cosine function going to equal 1/2. So for what value of 4x is your cosine function going to equal 1/2? So go look at the unit circle and tell me, where do you think your cosine function is going to be 1/2 at? What angles? And again, I know I've kind of written over it, but if you can from here, that's fine. If not, open your own unit circle. All right, Lucy, I've got pi over 3, 5 pi over 3. Savannah, same answers. Yeah, very nice. And we've kind of used that same cosine value for a multiple different examples now. So you can see cosine is 1/2 at pi over 3. Cosine is 1/2 at 5 pi over 3. So those are the angles we are using. Let's go back here. Very nice. So you are going to say, probably want to do this in two different answers. So we will say 4x equals pi over 3, or 4x equals, what was the other one? 5 pi over 3. Since they did not ask us to find these answers in the interval, specific interval, you are actually finding the generic or the general rule. So since this is a cosine function, your period is 2 pi, so you will actually add 2 and pi to both of these answers. Okay, go ahead and solve for x. And what are the x values going to come out to be when you get rid of that 4 on the left-hand side? So get x by itself, get rid of the 4, and what will your final answer end up looking like? So have your answer ready. Don't send it just yet. I want to give, again, everybody a chance to simplify that x value, and then we'll see what you guys come up with. Because, ultimately, whenever you're solving the equation, it's the variable, the unknown that you're trying to solve. So that's why we need to get rid of that 4 and just get x by itself for that final solution. So give you guys another couple seconds over here. Okay, let's see those answers, guys. Okay, let's see, Lucy, I've got pi over 12 and pi over 2, 5 pi over 12 and n pi over 2. Darren, you've got 5 pi over 12 plus pi n over 2, okay. It looks like pin, but I know that's what you have. And then pi over 12 plus pi n over 2. Okay, so I think same as Lucy's answers. So yeah, very nice. Let's do this in red. So basically, of course, we're dividing both sides by 4. So again, you can kind of think of this as dividing by 4 or multiplying by 1/4. So that means what you will end up doing over here is, pi over 3, but then the denominator gets multiplied by 4. And then 2 and pi will, of course, get divided by 4. On the other side, 5 pi over 3, but again, denominator gets multiplied by 4, plus 2 and pi divided by 4. So when you clean this up, as you guys had the answers over there, pi 3 times 4, of course, is 12, plus 2 and pi, actually, you know what? Let's go ahead and clean that up. 2 will go into itself once, go into 4 twice. 2 will go into itself once, go into 4 twice. So that will actually end up giving us, like you guys had, n pi over 2. And then for the other one, you had x equals, let's see, 5 pi over 12 plus, again, n pi over 2. And this will end up becoming our final answer for this equation. So just your multiple angle, when you had something like 4x as your angle measurement, and then how did you clean that up? All righty. Did anybody have questions on this example here? So really it's that extra step at the end, right? Just getting rid of that 4 on your x. All the other part of the problem actually stays the same. So that part does not change. Okay, let's save this guy. We'll clear him out. And just for extra practice, I thought We could do one with this, division, like the x divided by 2. So as you can see, we've got some examples here. Let's do 48 with the tangent function. So this guy is giving us tangent of x over 2 plus square root of 3 equals 0. So obviously start by subtracting and moving that square root of 3 to the other side, leaving us behind with tangent of x over 2 equals negative square root of 3. So, if it helps, think of tangent as sine divided by cosine. Where will you get negative square root of 3 when you divide sine by cosine? I mean, you can kind of think of it like this. So again, if it helps, look at the unit circle. Where will we get negative square root of 3? And since you are doing sine divided by cosine, I'm going to show it to you on the right-hand side, even though it's not the right side for this, because you have a negative square root of 3. The idea is you have to divide sine by cosine. So when you divide sine by cosine, do you get negative square root of 3? Obviously, it's not going to be this one here because there's no square root of 3 here. Sine divided by cosine, again, will that give me negative square root of 3? So that's kind of what you are looking at for these angle measurements and trying to see what you will end up getting as your answer. So for which angle measurement are you going to end up getting negative square root of 3? Okay, I've got Lucy, 2 pi over 3 and 11 pi over 6. 2 pi over 3. Okay, so 2 pi over 3. Let's change the color. Is this angle here, which means you're looking at these two. So we end up doing square root of 3 halves, divide that by negative 1 half. Now I'm just going to use algebra to help out. So keep the first fraction the same, change multiplication to division and invert the second fraction. So 2 will cancel out, leaving us with negative square root of 3. So this angle works. And then which one did you have? 11 pi over 6. So 11 pi over 6 will actually be taken care of in the general solution, because remember how tangent has a period of pi. So you actually only need to find the initial angles between 0 and pi. With sine and cosine, because the period is 2 pi, that's why we go the entire circle. But looking at the two sine and cosine values, are we going to get? Because you're taking negative 1 half and dividing it by square root of 3 over 2, which will be negative 1 half and then 2 over square root of 3. So you will see actually in this case, we get negative 1 over square root of 3. So the 11 pi over 6 is actually not going to work out. It's actually going to be this guy here. That works. So, just a little tricky thing, but like I said, because of the period being just pi, you just need to look at the upper half of your circle. Does that make sense, guys? Yeah, okay.
Yeah, that does.
Okay, all right. Let's get rid of some of this extra writing in here. So we know the 2 pi over 3 that you had definitely works. Let's get rid of him. So you will end up with 2 pi over 3. And then since the period is pi, you will add the n pi for your general solution. And then, of course, the only thing left to do is get x by itself and get rid of that division by 2. And, you can kind of think of this as scratch work if you like. So again, guys, go ahead and tell me, what do you think your final x should be once you get rid of that denominator of 2? And don't hesitate to ask a question if you don't understand anything or if you are stuck on something, because, obviously we want to make sure you guys are going to be comfortable solving these examples. So what's our x over here?
Is it -2 square root over 3?
-2 square root over 3. Okay, how are you getting that?
Oh, never mind.
Okay,
Yeah, I
because
was looking at the wrong thing.
Oh, okay, because all you want to do is get rid of that 2, right? Which means since you're dividing by 2, we will take, and if it helps, you can think of that as 2 over 1. You multiply both sides of your equation by 2 over 1. So that way, you know what, let's do it one line underneath so I'm not squishing everything there. Okay, so this is what we have. And we are trying to get rid of that 2. So we multiply both sides of our equation by 2. So this helps us get rid of the denominator. You get nice and clean x by itself. And then you're multiplying by 2, which means, remember to distribute that. And if it helps, write it as 2 over 1. So 2 times 2 will give us 4, right? 4 pi over 3 for this guy. Andrew, yeah, very nice. And then, of course, the n pi will end up becoming 2n pi. So you end up getting 4 pi over 3 plus 2n pi for this guy. And this will be your final answer. And again, since this is in the general format and not a specific interval, that's why we added the n pi to it. Questions on this one here, guys? Okay, so just a different form of that multiple angle equation. Let's save this, clear him out. And then one other type of problem that I wanted to show you. Let me see, what was the other example I selected? Yeah, it's based off of this one over here, where they're talking about how we can also use inverse functions to help us find a solution of a trigonometric equation. So as you can see, we are given here secant squared of x minus 2 times tangent of x equals 4. We, of course, go ahead and move that that 4 to the left-hand side, get 0 on the right-hand side. And then we will also go ahead and rewrite that secant squared of x using the Pythagorean identity as 1 plus tangent squared of x. Go ahead and multiply the 1 and the -4, which gives you the -3. We used factoring to simplify it. You take each factor and set it equal to 0, and you can see they're saying you're basically going to obtain 2 solutions, which is going to be in the interval of -pi/2 to +pi/2, because remember that is the range of the inverse tangent function. So you might have to kind of go back to chapter 1 for a little review for this. Now you're basically ending up with tangent of x, move that 3 to the other side. So to get x by itself, we use the tangent inverse function or the arctangent. So that's how you end up getting x equals arctangent of 3. And then same thing over here, you will get tangent of x equals -1, which will give you x equals arctangent of -1. And then based on that, we should be able to come up with a solution. This guy does not give us a nice clean answer. So we leave it as arctangent. And again, remember tangent has a function of pi. So that's why you're adding n pi to the generic answer. And then arctangent of -1 gives us a nice clean answer, -pi/4. So you end up with -pi/4 plus the n pi for the general answer. So in this case, again, you start out solving this like we normally did all the other examples. The only thing is when you get down to this final step, you're not able to get answers on its own. So this is where we bring in the inverse functions to help us out. So just to have another example, you've got example number 9 that you can look through in the video lectures, but let's pick an example to do from our textbook over here. And I think I had picked number 67 for this guy. So let's do 16(7). Cotangent squared of x minus 9 equals 0. So of course, we want to start by isolating the function. Go ahead and add the 9 to the other side. With cotangent, what can we do? Which identity can we use here? And you can always go back to your 2.1 handout to try and find those identities. Okay, Andrew, you're talking about Pythagorean. So for the Pythagorean one, it would be this one, or you said quotient. Cosine over sine, which would definitely be this. And Lucy, you also went with this one. So this one over here, and again, this may be a little bit of a trial and error to do, when you guys are working in your homework. But I would actually start out with, let's get rid of some of these marks. Writing this as 1 over tangent squared of x over 9. And the reason we are doing that, and you could kind of do it with cotangent here, but it'll be easier with tangent. Again, using simple algebra, you can use cross multiplication to switch those places out. And you will end up with 1/9 equals tangent squared of x. And here we will actually use the square root property to get rid of that square, because actually by bringing in the Pythagorean identity that a couple of you mentioned, you're actually going to make this more complicated than we need to. So since 9 is a perfect square number, right? 3 times 3, we can actually use the square root property over here. So let's go ahead and take a square root. But the only thing you have to remember here, guys, is that with the square root, you get 1 positive and 1 negative answer. So please be careful. That will help us get rid of the square. You will be left behind with tangent x, and then plus or minus, square root of 1 is 1, square root of 9 is 3. So you are getting tangent of x equals plus or minus 1/3. And then remember, this is where we bring in the inverse functions. So you will actually end up with tangent inverse. Take that on both sides. I'm trying to see how I want to write this. Tangent inverse of plus or minus 1/3. So this will end up giving you x equals plus or minus, do I want to say it like this? Tangent inverse of plus or minus 1/3. Or you can write it out as arctan, doesn't matter. So x equals tangent inverse of 1/3. And then remember the period of the tangent function is pi, or x equals tangent inverse of negative 1/3 plus n pi. Can we clean up any of these tangent inverse of a positive 1/3 or tangent inverse of negative 1/3? And this should be something you should be able to plug into your calculator and see if you get a nice clean answer or not. And if you don't, leave it as it is. That should be tangent inverse, not tangent. Okay. Did anybody get a neat and clean answer for any one of those numbers? No, Lucy, I see shaking your head. Andrew, you're shaking your head. Okay. Yeah. So in this case, kind of like it happened in our example over here. How this guy came out to be 1/4 or negative 1/4. That's actually not going to happen in our example. So you will actually leave this in this general format. So this will actually be our final answer. X equals tangent inverse, or like I said, if you wanted to, you can write these guys as arctangent also. Of 1/3 plus n pi and arctangent of negative 1/3 plus n pi. Alrighty, so that should be a negative there. Anybody have question on this guy? Okay. This one over here is actually talking about how you can use the quadratic formula. Remember, the quadratic formula is x equals negative b plus or minus b squared minus 4ac, and then the whole thing divided by 2a. In this case, your a, b, and c is actually coming from the quadratic equation here. So you will see how this is sine squared and this is sine. So they are the same trig function, right? It's not like you're having to switch in with sine or cosine, kind of like the first example we had done today. So here you actually have a format of a quadratic equation, which is going to be in the form of ax squared plus bx plus c equals 0. The only difference is instead of x, that's going to be a trig function. So like you have sine x over here. So in this case, what you want to do is you want to think of that leading coefficient as your a value. So we would say a equals 1. The middle coefficient, b, is going to be negative 3. And then the constant term is your c, which is negative 2. So remember, the square term always goes with the a. The single term goes with the b, which is your middle term. And then, of course, the number without any function on it, the constant term, is going to be your c. So that's where you get your a, b, and c values. And then instead of having, x over here, this will end up becoming sine x or, cosine x or, whatever the function might be given to you in the equation. But the right-hand side will be the same. So you will see this is negative b. So the negative from the formula, and then b itself was negative. So that's why you have two negative signs here. The two negatives will become positive. Then you do b squared. So that's the b squared minus 4 times ac divided by 2a. So literally using that formula, clean up the radical, which is coming out to be square root of 17, and then the denominator becomes 2. So you are getting sine of x equals 3 plus or minus square root of 17 over 2. To solve this, you will actually use the inverse sine function again, the arc sine, as you can see over here. So what they started out with was just simplifying with the plus sign and the minus sign, what these numbers come out to be. The range of the sine function we know goes from -1 to +1. So that's why we are saying, since this number here is larger than +1, you're not going to have a solution for this guy. So that's why this one has no solution here. The 3 minus square root of 17 over 2, since that number is between our range, we are able to find an approximate solution for this by using the arc sign. So you actually end up doing arc sign on this equation, which ends up giving you this value of negative 0.5963. And this one again is not a generic because they wanted us to stay within this interval. So that's why, you know, we are going with this approximation over here. And you can kind of see what that answer is coming out to be. And they're kind of showing it to you on the sine curve also, where you can find that solution that we were looking for. So you know how you can actually use the quadratic formula also to help you solve a trigonometric equation like this. So, you know, I mean, we get into trigonometry and we think, oh, this is so different from algebra, but you know, a lot of your techniques are still algebra based. You know, instead of just using X and Y as your variables, you end up using these trigonometric functions as your unknown variables, at least for a while. Here's another example, and I just thought this was a neat example of showing you how we can use trigonometry in a application. So this one is just, you know, it's giving you the equation and then it gives you some of the values and you're just literally simplifying it. So here's the equation. They're telling you where your theta value is between 0 and 90 degrees, so the first quadrant. Then they're telling you where the height is 2.4 inches. So that's the H value here, where your S, which is the, that's not the surface area. The side, I think, of the honeycomb is 0.75 inch. So that's the S you have over here. So, you know, you literally plug in those values into your equation, and then you're trying to figure out, you know, what the value of theta is going to be. So you can kind of see how we plug those numbers in, you know, try and clean up our equation as we can. And then you're basically going to use a graphing calculator to help you out in this case. And so you actually use the built-in minimum function to figure out what is the lowest possible angle that we can get, you know, where this equation is concerned, and you will end up with 54.7356 degrees. And, you know, of course, since they told us your theta is going to be between 0 and 90 degrees, we know we were leaving our calculator in the degree mode. So just an application problem to kind of help you guys out working through this. So, you know, look through that. But solving these equations is, you know, obviously the big part of section 2.3. So you've got various different examples in your homework to kind of go through that you should, you know, definitely try working on, and let me know if you have any questions. So that was 2.3, and that's a fairly long section because, you know, you have so many different types of equations that you have solved. Now, section 2.4 and section 2.5 are actually based on these little formulas that we have here. So how can we use the sum and difference formulas based on, are you using sine, cosine, or tangent function, you know? And in this case, you will actually see that instead of just having a single, you know, sine of X, you actually now have either U plus V, U minus V with the sine, cosine, and tangent. And then you actually have this formula of how you actually simplify a given function where you have the plus and the minus sign in that. So we will not have too much time to spend on this, but I just want to show you at least a beginning example to get you guys kind of thinking about this. They're talking about if you want to see proofs of how they came up with these different formulas, you can actually see that in your textbook on page 257, if that is something you are curious about. So it's part of your textbook you can go look at. But let's take a look at this first example over here, how we can actually bring in this idea of sum and different formulas to help us simplify some of these. So look at this example here. This one is just sine of pi over 12. Well, sine of pi over 12, you know, obviously there's no U plus V or U minus V situation. That is what we have to create. So how can we break down that angle pi over 12 so that we can, try and find an exact value for it? So you will see we're actually using this idea of taking pi over 12 and rewriting it as pi over 3 minus pi over 4. And, again, this is just using algebra. If I find a common denominator, well, that will be 12. Multiply this guy with 4. Multiply this guy with 3. You get 4 pi minus 3 pi over 12. 4 minus 3 is 1. That's your pi over 12, and you come up with that. So it's just how you can break down your single angle. And then I can rewrite the sign of pi over 12 as sine of pi over 3 minus pi over 4. And this is where your sine of u minus v formula will kick in, because you have, pi thirds minus pi fourths. So that's where this formula will come in. So you can see this is sine of u, which is the first angle, cosine of v, which is the second angle, and then you basically reverse that. If this is a minus here, this is a minus here in the sine function. And then now you have cosine of u and sine of v. So you basically go sine of u on the first one, which becomes sine of v on the second one, cosine of v on the first one, which becomes cosine of u on the second one. And then once you break that down using that formula, this is what this breaks down into. And now using unit circle, we know sine of pi over 3 is square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. So that helps us break down the first part. Again, minus, minus. Cosine of pi over 3 is 1/2. Sine of pi over 4 is square root of 2 over 2. We can now go ahead and clean these guys up. Square root of 3 times square root of 2 gives you square root of 6. Again, we've got that minus sign here. 1 times square root of 2 is square root of 2, and then denominator 2 times 2 and 2 times 2 gives you 4. And just to check and make sure that you have the right answer, put this into your calculator and put the sign of pi over 12 into your calculator, and you get a decimal approximation. The difference here is, guys, they wanted an exact answer, not a decimal answer. If they just said, find sine of pi over 12, this guy would have worked. However, since they said exact, that's why we had to do all of this mess over here, because they wanted to know what the exact answer would be for sine of pi over 12. And, of course, as we know, pi over 12 is not really a given angle in a unit circle. So that's why we have to go through this process here. So that's kind of what this section is going to be dealing with, is how we can use these properties of sum and difference formulas to kind of figure out some of these angle measurements. So you can see here, same thing, we're using pi over 12. We did sine in this example. This one is cosine. So you can see the explanation for this in the video lectures. And then we're just going to break this down into radians and degrees, because this formula will work for no matter what mode your angle is in. And you can see this example here with 75. It was easy to break this down into 30 and 45. So 30 plus 45. So you're using the sum formula, cosine of u plus v. So use that to break this down. And then again, using the unit circle, we were able to come up with an answer. They're telling you another way to solve this would also be breaking down 75 degrees into 120 minus 45. And then you could use the cosine of u minus v formula instead of the cosine of u plus v. But the key thing you want to do when you're working with these types of examples is try and stay within these known angle measurements. So, that's why we are using pi over 4 and pi over 3, or, we did the 45 and the 30 degrees. So you want to try and stay within the given angles on the unit circle, because then, you don't have to go calculate that value. You can just use the unit circle to help you out. So what we will do for class on Wednesday is look at some of these examples. This is not a very big section like 2.3. This is a fairly small section. So we'll try and look at examples from here, do a few different ones. And then this is actually continuing with formulas, but here we're getting into multiple angle formulas and, product to sum. So you will actually see with the product to sum what those look like. So half angles, the power ones. So just different formulas and how we can use them to simplify, some of these examples. So that's what we'll kind of focus on Wednesday. So if you guys have any questions, feel free to stay behind and I'll be happy to answer them. And if not, guys, I will see you on Wednesday. Like I said, I'll answer those questions you've already sent me through WebAssign. And if you have any new ones, obviously go ahead and forward those also. So have a wonderful evening, guys. Be careful, and I will see you on Wednesday. Take care, everyone. Stay safe. Thank you.